Our task is to decompose the given expression into partial fractions. The first thing is to rewrite the numerator following the denominator. What I meant by that is to write x cubed plus 9x squared plus 7x plus 32 into x cubed plus 3 times x squared plus 4x plus 12, and then plus whatever's remained. What this does is it enables us to extract a 1 out of the original expression. So we get 1 plus some fraction, where the numerator is now a second order polynomial, while the denominator is the original third order polynomial. Next, we proceed to factorize the denominator. Problems like this usually have a simple root, which might be found just by observation, but if you are unable to do so, you can also stick to the rational roots test. The idea is that if a root exists, one of the rational roots of a polynomial is related to the factors of the leading and trailing coefficients. Here the leading coefficient is 1. Its factors are plus and minus 1. For now we denote its factors by the alphabet Q. And the trailing coefficient is 12, so it does have more factors as shown. We denote these factors by P. A rational root can be found among all combinations of P over Q. So after some testing, combining every possible pair of P and Q, you would discover that x equals minus 3. So therefore, we can rewrite the denominator as the product of x plus 3 and some second order polynomial. For now, we use a, b, and c to represent the coefficients of the second order polynomial. So one way to solve for a, b, and c is via synthetic division. We actually have demonstrated synthetic division in a few other videos. If you are interested, please refer to those videos. The links will be provided in the video description below. For now, I just want to show an alternative method. The method is by simply opening up all parentheses. After grouping all the like terms, we obtain a third order polynomial with a, b, and c as coefficients. Because this must be equal to the original denominator, which is a third order polynomial, the coefficients at the equivalent locations must match each other. So let's say for x cubed, because its coefficient is 1, and here the coefficient is a, then a must be equal to 1. Moving on to the next variable, 3a plus b must be equal to 3 for x squared. So we get b equals 0 in this case. And then same idea can be applied for c, and we get c equals 4. Therefore, the original denominator is the product of x plus 3 and x squared plus 4. And because x equals minus 3 is the only root, and that x squared plus 4 is up to the second power in x, this whole thing is considered a non-repeated quadratic factor. What it means is that we should have two fractions after the decomposition. So because x plus 3 is up to the first order in x, its numerator should be 0 order in x, which makes it just a number or constant. We use a for the representation. And in the case of x squared plus 4, because x is up to the second order, so the numerator should be up to the first order in x, which can be expressed as bx plus c. So this means that the original numerator must be equal to what we have on the right hand side of this equation. This is obtained by cross multiplication and addition of the two terms. So in order to solve for a, b, and c, we can use the same method as before by expanding the right hand side and then group all the same terms. So this gives us a set of equations where 6 equals a plus b, 3 equals 3b plus c, and 20 equals 4a plus 3c. And then solving the equation set simultaneously by a substitution, we obtain a equals 5, b equals 1, and c equals 0. So in summary, the original expression given in the problem statement can be decomposed into 1 plus 5 over the sum of x plus 3 plus x over the sum of x squared plus 4.